Welcome to Lecture 2. In this lecture, we will talk about the idea of linear systems of equations. And let's just begin with an example. Let's suppose that we have the following system of equations: x plus y plus z is equal to 6, 2x minus y plus z is equal to 3, and 3x plus y minus z is equal to 2. And we want to know what x, y, and z are. Now, first of all, this is a system of equations, and these are linear equations. And what we mean by that is that if you look at these equations, in every one of them, the unknowns appear only to the first power. We have x to the first power, y to the first power, and z to the first power. We don't have any other powers of the variables. We don't have the variables multiplied by each other. And so these are all linear equations, and we have 3 equations and 3 unknowns, and we expect, or we hope. Now, just because you have 3 equations and 3 unknowns, that does not guarantee that you can solve it. Let me give you an example, a quick counterexample of that idea. Suppose we had x plus y equals 2. Well, we'll say, since I had 3, it's my example, I'll say, suppose we had x plus y plus z is equal to 4, 2x plus 2y plus 2z is equal to 8, and 3x plus 3y plus 3z is equal to 12. Well, that's 3 equations and 3 unknowns, but you can't solve that for x, y, and z because those are not 3 independent equations and 3 unknowns. In fact, those really are just one equation. They're the equivalent of just one equation, because the second one is simply twice the first equation, and the third equation is simply 3 times the first equation. So really you only have one independent equation there and 3 unknowns, and therefore you cannot solve that. So I'll just put a big X through this. So that's just to emphasize that just because the number of equations is equal to the number of unknowns, that doesn't absolutely guarantee that you can solve it, but at least it gives you some hope that you can solve it. If the number of equations is less than the number of unknowns, then you definitely cannot find a unique solution. But in this case, we do have the number of equations equals to the number of unknowns, and so we hope that we might be able to solve it. And so what we're going to begin this lecture with is a discussion of a systematic way of solving, or at least trying to solve, a system of equations. And the idea that we're going to be talking about is called Gaussian elimination. Now, the first step in this procedure, if you want to cover all of the bases, is to rewrite this system of equations as a matrix equation. Now, really, to be honest with you, you're not going to need to do this in the future. But for this first time, I would like to show you every single detail. So let's see how that would go. The system of equations that we have here is equivalent to the following: 1, 1, 1, 2, negative 1, 1, 3, 1, negative 1, x, y, z equals 6, 3, 2. Now, here we have, let's look at this and make sure you understand exactly what I'm saying here. This is a 3 by 3 matrix. And this is a 3 by 1 matrix, which is also called a column vector. And here's another 3 by 1 column vector. This is a known column vector. It's known because we know all the components of it. This is an unknown vector because the components of this vector are unknown variables that we're trying to solve for. And again, let's observe. This is 3 by 3, and this is 3 by 1, and this is 3 by 1. And so you see that this multiplication does turn out correctly because here these threes match, so it tells you that this is a legitimate matrix multiplication. And furthermore, when we multiply this 3 by 3 system matrix by this 3 by 1 unknown vector, the dimensions of the result will be 3 by 1, which is in fact exactly what we have over here on the right hand side, 3 by 1. And if you multiply out both sides using our rules for matrix multiplication that we had before, you will see, I'll just write it over here. Okay, we multiply across the first row and down this column, and our first entry would be x plus y plus z. Then multiply across the second row and down this column, and we would get 2x minus y plus z. And then multiply across this final row and down this column, and we would get 3x plus y minus z. So that would be the 3 by 1 matrix that we would get on the left hand side. And then on the right hand side we simply have 6, 3, 2, which is also 3 by 1. So now we have that these two 3 by 1 matrices are equal to each other, and of course that means that every component is the same. So that says that x plus y plus z is 6, 2x minus y plus z is 3, and 3x plus y minus z is 2. But those three equations that I just listed are exactly the three equations in our system of equations. So that proves that's why we say that this system, this single matrix equation here that we've written down is equivalent to the original system of equations. And once again, I emphasize that you won't ordinarily have to explicitly write down this matrix equation corresponding to your system of equations, but this first time I think it's good to do so just to make sure you understand exactly where everything is coming from. Now, once you have this matrix equation, then you want to form something, and by the way, once again, I used this term already, but this matrix right here is frequently called the system matrix. Okay. So now for Gaussian elimination, I'll say first step, form the augmented matrix. Now, what is the augmented matrix? Well, it is simply the system matrix, 1, 1, 1, 2, negative 1, 1, 3, 1, negative 1. So that's the system matrix. But now we put, some people like to put a dashed line. Some people don't put any line at all. But you want to put one more column here, and the other column will be the right-hand side. And that's, some people just call this right-hand side. Some people will call it a forcing vector. You'll see different names. But this is the augmented matrix down here. You see that you have the system matrix on the left and the forcing vector, or the right-hand side, whichever you wish to call it, on the right. And this dotted line is just for your convenience to help remind you that these things are separate from each other. And so this is the augmented matrix. And now what we want to do next, second step, using Gaussian elimination, eliminate all non-zero terms below the main diagonal. Now, first of all, what is the main diagonal? Well, if you start in the upper left-hand corner of your matrix and then just go down diagonally, you get the main diagonal. So in this case, for this matrix, our main diagonal is right there. It is this 1, -1, -1. That's our main diagonal. And we see that at the present time we have 3 non-zero terms below that main diagonal: 2, 3, and 1. All of these are non-zeros. So so we have 3 non-zero terms below the main diagonal, and we would like to use Gaussian elimination to eliminate those numbers. And so what is Gaussian elimination? Well, let's just say allowed procedures in Gaussian elimination. There are 3 different procedures that you can employ in Gaussian elimination. The first of these is to interchange any 2 rows of the augmented matrix. In other words, if we look here at our augmented matrix, if we wished, we could interchange, for instance, the first row and the second row, or the first row and the third row, or the second and the third, the second and the first. Any one of those exchanges would be fine. The second procedure is that we can multiply any row by any non-zero number. So, for instance, we could multiply the entire second row by 7, or we could multiply the entire third row by 3.4, or whatever we wished. The only number we can't multiply a row by is 0. And 3, and this is the procedure that you will use most often, we can add any multiple of any row to any other row. And using just these 3 procedures, we will be able to take this augmented matrix and eliminate all these three non-zero terms below the main diagonal. And then once we've done that, solving the original system of equations, which we have right here, will be trivial. And the last thing I want to point out before we proceed is that these three techniques, if you wish, you can memorize this list of procedures or techniques that you can use in Gaussian elimination, but there's really not much to it. I mean, just remember that each row of the augmented matrix simply corresponds to one of your equations. Here are the equations up here, and here's the augmented matrix, and you can see that x plus y plus z equals 6. Well, that's just represented by this first row, 1, 1, 1, and 6. The second equation, 2x minus y plus z equals 3, that's represented by 2 minus 1, 1, 3. And then the last equation, 3x plus y minus z equals 2, is represented by this last row, 3, 1, negative 1, 2. And once you've realized that the augmented matrix then is just a compact way of rewriting the system of equations, then it's certainly not surprising that we could interchange any two rows of the matrix without changing the basic system of equations. Because, of course, if we interchanged any two of these equations, for instance, if we wrote the last equation first and the first equation last, that certainly wouldn't change the solution. Or if we wrote the third equation second and the second equation third, that wouldn't change it either. So the first procedure here is certainly not surprising, nor is the second one, that we can multiply any row by any non-zero number. For instance, we could multiply this entire first equation by 2 and have 2x plus 2y plus 2z equals 12. That is still basically saying the same thing as this first equation, and so it would not change the system of equations. And finally, it's not too surprising either that we can add any multiple of one of those equations to another one of those equations, and that's the equivalent of what we're doing here when we add any multiple of any row of the augmented matrix to any other row of the augmented matrix. So these procedures are really not anything that's real news to you. I think you're aware of all of them, but it does maybe help to have them all grouped together. So now, using these procedures, and only these procedures, we want to see how to eliminate the non-zero terms below this main diagonal, and furthermore then how that will allow us to easily solve the system of equations. So let's copy this system, copy this augmented matrix, and then proceed. So there's the augmented matrix. And let's see what happens. Okay, now the key to doing the Gaussian elimination procedure is to eliminate these non-zero terms below the main diagonal, and we're going to go from top to bottom and from left to right. And you'll see what that means right away. So going top to bottom and left to right, that means that we're first going to eliminate this 2, then we're going to eliminate the 3, and then we're going to eliminate the 1. Now, how do we eliminate the 2? Well, the easiest way to do that is to add to the second row of the augmented matrix -2 times the first row. This is a matter of employing procedure number 3, which says add any multiple of any other row add any multiple of any row to any other row. So we're going to add -2 times the first row to the second row. Okay, now let's see what happens when we do that. So we're not really affecting the first row at all. So it stays at 1116. But now we're going to add negative 2 times the first row to the second row. And let's see what happens. Well, negative 2 times 1 is negative 2. And when we add that to 2, we will get 0. Negative 2 times 1 is negative 2. And negative 2 and negative 1 is negative 3. Negative 2 times 1, again, is negative 2. Negative 2 and 1 is negative 1. And negative 2 times 6 is negative 12. And when we add that to 3, we get negative 9. Now, if you wish, we could go ahead and write down the third row. In fact, I guess this first time through, I'll go ahead and do that. And so that would be the first step of the Gaussian elimination procedure. And notice that if now the main diagonal of the augmented matrix is right here, 1, negative 3, negative 1, and whereas we originally had 3 non-zero terms below the main diagonal, now we have just 2 non-zero terms below the main diagonal. This is a 0, so it doesn't count. So we're left with just 2 non-zero terms below the main diagonal. Now, continuing to go from top to bottom and from left to right, our next objective is to eliminate the 3. And how can we do that? Well, we eliminate 3 by adding negative 3 times the first row to the third row. So we're left, again, we're not changing anything in the first row, so we have 1116. And this time we're not changing anything in the second row, so we can go ahead and write down 0, negative 3, negative 1, negative 9. But for the third row, we're adding negative 3 times the first row to the third row. So negative 3 times 1 is negative 3, and 3 gives 0. Negative 3 times this 1 is negative 3, and 1 gives negative 2. Negative 3 times this 1 is negative 3, and negative 1 gives negative 4. And negative 3 times 6 is negative 18. And add that to 2, and you get negative 16. And so at the end of this second step of Gaussian elimination, we would have this augmented matrix right here. And now you can see here is the main diagonal. And now we have only one non-zero term below the main diagonal. Now, before I go any further, let me state that after you've done this a few times, you would almost certainly choose to do these first two steps together. In other words, instead of writing down these as two separate steps, you would combine them all into one. You would have added negative 2 times the first row to the second row. And so when you do that, okay, here you would have written down the same first row, and then you would have written down this for the second row. And then rather than writing down the third row like this, and then having to write everything over again, you would have gone ahead and said, okay, and now to get rid of the 3, I'll add negative 3 times the first row to the third row. And so you would have jumped to this step immediately rather than having to have this intermediate step. But for this first time, there's certainly no problem with going step by step. But as it was pointed out just a moment ago, we still have one non-zero term below the main diagonal, and we want to know how to eliminate it. Now, you might be thinking that you'll now take 2 times the first row and add it to the last row, because 2 times this 1 would give us a positive 2, and then when we add it down here, we would get 0. But we don't want to do that, because if we took 2 times the first row and added it to the third row, then we would get a 2 times 1 would give 2 plus 0, and we would introduce a 2 here. So we would mess up this 0 that we have right here. Instead, what we want to do is add a negative 2/3 times the second row to the third row. This won't mess up the zeros here, but it will introduce a zero here. So the theme here is that when you're eliminating terms in the first column, you do that by adding multiples of the first row to lower rows. When you want to eliminate terms in the second column, you do that by adding multiples of the second row to lower rows. And likewise, if you had a bigger system, you would keep up that same pattern. If you want to eliminate terms in the nth column, you do that by adding multiples of the nth row to lower rows. So, again, to eliminate this negative 2 here, what we will do is add to the third row negative 2/3 of the second row. So the first row is not getting changed. We have 1, 1, 1, 6. And the second row will stay as 0, negative 3, negative 1, negative 9. Oh, and by the way now, okay, when we start, we've said just now that one way to do this would be to multiply the second row by negative 2/3 and then add it to the bottom row. Okay, this is certainly a way to do things. I don't particularly like that way because that's going to introduce fractions into our augmented matrix. And I think that once we start dealing with fractions, then it increases the probability of error. But I'm going to go ahead and do it this time. But after I've done it, I'll show you another alternative. Okay, so again, multiplying the second row by negative 2/3 and then adding to the third row, let's see what happens. Well, negative 2/3 times negative 3 will give us a positive 2. And when we add positive 2 to negative 2, that'll give us a 0 here. And of course, negative 2/3 times this 0 is 0 plus 0 is we have a 0 here. And then negative 2/3 times negative 1 will give us a positive 2/3. And a positive 2/3 and a negative 4 will give us a negative 3 1/3, or negative 10/3. So negative 10/3 here. And let's check that one more time. This is negative 12/3. And then when we multiply this by negative 2/3, we get a positive 2/3. So 2/3 and a negative 12/3 is indeed negative 10/3. So that looks good. And then when we multiply negative 2/3 times negative 9, we get a positive 6. And then 6 and negative 16 is negative 10. So this would be, if we use the three procedures here, actually what we've done is just to use procedure 3 over and over. And if we do that 3 times, then we arrive at this augmented matrix right here. Notice that our main diagonal is 1, negative 3, negative 10/3, and everything below the main diagonal is a 0. And so we have achieved the goal of eliminating all non-zero terms below the main diagonal. And now how do we finish this? Well, let's write down the system of equations. It's just like in the beginning. We started with a system of equations. And from this system of equations that we had right up here at the beginning, we obtained the augmented matrix. Well, now we're going to go backwards. Here's our augmented matrix, and we write the corresponding system of equations. So the first line is x plus y plus z equals 6. The second equation is negative 3y minus z equals negative 9. And the last equation is negative 10/3 z equals negative 10. And notice that the last equation is just one equation and one unknown, and it immediately implies that z is equal to 3. And then this stage, what we're going through right now, is called back substitution. Now that we have obtained z, we go backwards and stick that into the second equation. Because the second equation has only y and z in it. So now that we stick that value of z in, we'll get negative 3y minus, and now we substitute for z, we substitute 3, and that gives negative 9. And that implies that negative 3y is equal to, when we add 3 to both sides, we'll get negative 6. And that implies that y is equal to 2. And now we take our value for z and our value for y and substitute both of those back into the first equation, and that will give us x plus 2 plus 3 is equal to 6, which implies that x is equal to 1. And so the final solution to our system is x equals 1, y equals 2, z equals 3. And let's go back to the original system of equations to check that. 1 plus 2 plus 3 is indeed equal to 6. 2 times 1 would be 2, minus 2 would be 0, plus 3 is indeed equal to 3. 3 times 1 is 3, plus 2 is 5, minus 3 is indeed 2. So all three of those equations checked out, and we conclude that this is indeed the answer to our system of equations. Now, before we go to another example, I'd like to return to an issue that I mentioned a bit earlier, which is, you recall that here in the Gaussian elimination procedure, we had some fractions arising, and as I pointed out at the time, I don't particularly like to have fractions arise in the matrix if it's easily avoidable, because I think that once you start dealing with fractions, then that raises the probability of making an error. So let me look at this very same problem again, but in a slightly different way, to show you how you could avoid that. So we'll start off again with 1, 1, 1, 6, 2, negative 1, 1, 3, and 3, 1, negative 1, 2. And I'll show you a couple of things this time. First, I'll show you what I meant when I said that we could combine the first two steps to jump immediately from this stage to the third stage. So let's see how that would go. Okay, again, we begin by identifying this as our main diagonal. And so the non-zero terms below the main diagonal are 2, 3, and 1. And we want to first eliminate 2 and then 3. So we'll keep the first row as it is, 1, 1, 1, 6. And then we want to eliminate the 2, so we will add negative 2 times the first row to the second row. And when we do that, okay, negative 2 times 1 is negative 2, and 2 gives 0. Negative 2 times this one is negative 2, and negative 1 is negative 3. Negative 2 times 1 is negative 2, and 1 is negative 1. And negative 2 times 6 is negative 12, and 3 gives negative 9. And now let's go directly to the next stage, which is to eliminate this 3. Notice we've eliminated the 2 now. Now let's go ahead and eliminate the 3. And we can do that by adding negative 3 times the first row to the last row. Negative 3 times 1 is negative 3, and 3 gives 0. Negative 3 times 1 is negative 3, and 1 is negative 2. Negative 3 times 1 is negative 3, and negative 1 is negative 4. And negative 3 times 6 is negative 18, and 2 gives negative 16. And so you see now that this matches the third step from above, and so that's how you would combine these two steps into one. Now at this point, this is, as I mentioned, this is exactly where we were above, and this was the stage at which we observed that the only remaining non-zero term below the main diagonal is negative 2, and that one way we could get rid of that negative 2 is by adding negative 2/3 times the second row to the third row. But suppose that you don't like that because of the fractions. Well, what else could you do? Well, what you could do, remember that you're allowed to multiply any row by any non-zero number. So what I'm going to do is I'll leave the first row as it is, 1, 1, 1, 6. I'll multiply the second row by 2 to get 0, negative 6, negative 2, negative 18. I'll multiply the third row by negative 3 to get 0, 6, 12, and 48. And you can see why I chose those numbers. I chose to multiply the second row by 2 and the third row by negative 3, so that now I would have negative 6 and 6 in this position, and it makes it very simple for me to go ahead and do the next step. So I'll get 1, 1, 1, 6. And now for this next step, well, let's just go ahead. So we'll have 0, negative 6, negative 2, negative 18. And now we add the second row to the third row. 0 plus 0 gives 0. Negative 6 plus 6 gives 0. Negative 2 and 12 gives 10. And negative 18 and 48 gives 30. And so now, when we pull that trick, this is what happens. And now if we write down our system of equations corresponding to this augmented matrix, we get x plus y plus z equals 6 minus 6y. Now notice, if you wanted to, before writing down the system of equations, you could multiply through this row by 1/2 if you wished, and then you would get back to this equation right here, but there's no need. It's just whatever you want to do. So negative 6y minus 2z equals negative 18, and then the last equation will be 10z equals 30. And of course that immediately implies that z is equal to 3. We plug that in to the second equation, and when we do, then we're left with negative 6y minus 2 times 3 is equal to negative 18, and that implies that negative 6y is equal to negative 12, which implies that y is equal to 2, and then we plug in z equals 3 and also y equals 2 into the first equation, and we get x plus 2 plus 3 equals 6, which implies that x is equal to 1. And so once again, we are coming up with the solution x equals 1, y equals 2, and z equals 3. Same solution as before, but this time we were able to avoid the introduction of fractions into our augmented matrix. So that's something worth knowing if you are like me and don't particularly like having fractions running around. So now what we'll do is have one last example, and then we'll look at some problems. Okay, our final example for this lecture will be this system of equations. X minus y plus z is negative 3. 2x plus y minus 3z is 11. And negative x minus y plus 2z equals negative 8. I encourage you in the strongest terms to now stop the video, try this on your own, and then we'll look at it together. Okay, so I hope you had good luck with trying to solve this system of equations using Gaussian elimination. And now we'll look at it together. And by the way, before I proceed, let me say, I know that some of you probably have calculators that will solve systems of equations, but we want you to understand the Gaussian elimination procedure. So don't merely depend on being able to use your calculator to do this. You want to understand the procedure itself. So make sure you go through these examples step by step. Okay, so now we'll do this all together. The augmented matrix corresponding to this system of equations is shown right here. And you can see that, as in the previous example, we have 3 non-zero terms below the main diagonal. That's 2, negative 1, and negative 1. So to get rid of the non-zero terms in the first column below the main diagonal, this 2 and the negative 1, that'll be our first goal. And so to get rid of the 2, we add negative 2 times the first row to the second row. Negative 2 times 1 is negative 2, and 2 is 0. Negative 2 times negative 1 is 2, plus 1 is 3. Negative 2 times 1 is negative 2, and negative 3 is negative 5. And negative 2 times negative 3 is 6, plus 11 is 17. And then to get rid of this negative 1, we merely add the first row to the last row. So 1 and negative 1 is 0. Negative 1 and negative 1 is negative 2. 1 and 2 is 3. Negative 3 and negative 8 is negative 11. And so this is where we get, after eliminating all the non-zero terms below the main diagonal in the first column. And now there's only one remaining non-zero term below the main diagonal, and it's this negative 2 here, and that's in the second column, so we should add some multiple of the second row down below to get rid of that. And of course, this is a similar situation what we had before. We could add 2/3 of the second row to the third row if we wished to get rid of the negative 2, but then that would introduce fractions into the augmented matrix. And so instead, what I've decided to do here, notice that the first row is exactly the same, but I've multiplied the second row by 2 to get 0, 6, negative 10, 34. And I've multiplied the third row by 3 to get 0, negative 6, 9, and negative 33. And then in going from here to here, I've done two things. I've added the second row. Well, first of all, the first row is untouched. So you can see it remains at 1, negative 1, 1, negative 3. The I've also added the second row to the third row, and so when I did that, the 0 plus 0 is 0, 6 and negative 6 is 0, negative 10 and 9 is negative 1, and 34 and negative 33 is positive 1. And the last thing I did was to return this second row back to its original form. In other words, you might say that I multiplied the second row by 1/2. So 1/2 of 0 is 0, 1/2 of 6 is 3, 1/2 of negative 10, sorry about this interruption, 1/2 of negative 10 is negative 5, and 1/2 of 34 is 17. I'll wait just a moment here. Okay, sorry about that. As you heard, I have some very annoying cats. So anyway, we arrive, if following that procedure, we arrive at this augmented matrix. Notice that we've eliminated all the non-zero terms below the main diagonal, so now we're ready to go back to the equation form. The first row corresponds to the equation x minus y plus z is negative 3. The second row corresponds to 3y minus 5z is 17. And the last row corresponds to negative z is equal to 1. So then the last equation easily is seen to imply that z equals negative 1. Plug that into the second equation and you readily conclude that y is equal to 4. And then plug both of those results into the first equation and you will conclude x is equal to 2. And so our final solution is x equals 2, y equals 4, and z equals negative 1. And if you substitute that into the equations here that we began with, you will see that that is indeed the solution to this system of equations. And so that's how we use a Gaussian elimination procedure to solve a system of equations. And now let's look at some problems for this lecture. Okay, the in-class problems for this lecture will be, the first one, 2.1, will be problem 7.3.3 from your text. And problem 2.2 will be 7.3.13 from your text. And then in class, we'll have one more problem related to this topic. So that concludes lecture 2, and good luck. Oh, and by the way, those weren't really cats.